Okay, so today's notes, we're looking at triple integrals again. We are learning another type of coordinate system, or another way of approaching triple integrals. So far we've looked at just regular x, y, and z plane. Then we've converted our x, y, z plane to cylindrical. We looked at the r and theta, and then z stayed the same. Spherical is something new. It's not related to anything that you've done before. So it's not like polar, it's not like cylindrical. If you convert coordinates to spherical coordinates, in 3 space, of course, there's going to be 3 different variables. Any point is listed as rho, theta, phi. Theta you've seen before. Theta is the same theta that you knew before. Rho is the distance the point is from the origin. And phi or phi, depending on how you want to pronounce it, is also an angle, like theta, but it's the angle between the positive z-axis and a point. Okay, so let's look at an example so you can see what these actually look like in space. Okay, so theta is the theta that you've seen before. Theta is on the xy plane, and it's the angle from the positive x-axis. Then what you're also going to have is you are going to have the angle from the positive z-axis. That's here, that's phi. And then the actual distance to that point is your rho. Okay, so visually, here's what you're looking at. You can picture this here. Theta is the one that goes like this. Okay? Phi goes like this from the z-axis. So you have your theta that will go over, you have your phi that will come down, and then you have your actual rho that will tell you the distance from how far to go. So you'll go sideways, then you'll go down, and then you'll go out however far you need to.
Is this only for spheres?
It's only in 3 space, yes. Yeah, you wouldn't look at spherical coordinates in 2 space. It is going to really only come into play when you're looking at triple integrals on a sphere of some kind. That's really the most helpful. Here are some things that you need to know, and these should intuitively make sense. Rho, of course, has to be at least 0. If you're looking at distance, it has to be at least 0. Theta, we've talked about, is between 0 and 2 pi, just like the theta that it always is. This is the one that might take a little bit more thinking. Phi is between 0 and pi. Between 0 and pi. And that's because if you went all the way to pi, that would be from the positive z-axis all the way down to the negative z-axis. So you're not going to keep going then, because
so
everything's...
Would be like positive z and then...
Correct. Yeah. Okay, so a few common graphs that we should be able to identify. First one, if we have rho is equal to some constant. Anybody know what that would be? Sphere. If we have theta is equal to some constant. This is not really a figure, but I'm going to call it a figure. So if you move your theta a certain amount, and then everything up or down, it's going to create a half plane. It's not really a figure, but the plane is going to extend one way, but not the other. Let's see if we get this one. What about phi is equal to some constant? Can anybody tell me what that graph would be? Cone. Yeah. cone. If that C is between 0 and pi over 2, it would be the top cone, like a cone opening up. But if C is between pi over 2 and pi, the cone would be on the bottom, so it'd be opening down. Before we even look at triple integrals, we're going to need to know how to convert between the two, how to convert between rectangular and spherical. So that's what we're going to do first. Converting. Here are the formulas that you need to know. X is going to be equal to rho sine of phi cosine of theta. Y will be equal to rho sine of phi sine of theta. And then Z will be equal to rho cosine of phi. Also, fun fact, this should probably make sense. Rho squared is equal to x squared plus y squared plus z squared. Okay. Questions?
Wait, what's that? Z equal, is that?
Rho cosine of phi.
Oh, plus or minus.
No, it's just my equal sign was unclear, so I drew it again. Bless you. Okay, can I keep going? Yeah. Okay, so first example. We are going to convert the point 2, pi over 4, and pi over 3 to rectangular coordinates. So using, well, first of all, before we do that, remember that pi over 4 is theta and pi over 3 is phi. So our x we wrote down is rho sine of phi cosine of theta. So that will give us 2 sine of pi over 3 cosine of pi over 4. So that's 2 times root 3 over 2 times 1 over root 2, which gives us the square root of 3/2. If you want to rationalize it, go for it. I'm not going to because I'm too lazy. Then our y is equal to rho sine of phi sine of theta. So that is 2 sine of pi over 3 cosine, not cosine, sine of pi over 4. Hopefully you can see again that would be the square root of 3 over 2. So our z then is rho cosine of phi. So that would be 2 times cosine of pi over 3, which is 2 times 1/2, which is 1. So that point in spherical could also be written as square root of 3/2, square root of 3/2, 1. We're going to do one more converting and then we'll look at some triple integrals. Second example, we're going to go the other direction. So this time our point is in rectangular. It's the point 0, 2 root 3, negative 2. And we are going to convert that to spherical coordinates. We're going to use the formulas that I gave you before. So rho squared is equal to x squared plus y squared plus z squared, which tells us that rho is going to be the square root of 0 plus 4 times 3 plus 4, which equals 4. Okay, so then we have the formulas for x, y, and z. The z formula is the least complicated one. We know that z is equal to rho cosine of phi. So what that tells us then is that cosine of phi is equal to z over rho. So we get cosine of phi is equal to negative 2 over 4, which is negative 1/2. That tells us that phi, where cosine is negative 1/2, is either 2 pi over 3 or 4 pi over 3. We don't need to think too hard about this one. Remember that phi is always between 0 and pi. So 4 pi over 3 cannot be our answer. Phi has to be 2 pi over 3. So then to find theta, we can either use the equation for x or y. It doesn't matter. There's not one that's better than the other. So I'm going to do the formula for x, which is rho sine of phi cosine of theta. So if I'm looking for theta then, this tells me that cosine of theta is equal to x over rho sine of phi. What's really nice here is x is 0, so that tells us cosine of theta equals 0. So we have 0 divided by some quantity. So our theta then has to be pi over 2 or 3 pi over 2. Like cylindrical, you can either consider the signs of your x and y. So in this case, we have a positive x and a positive y. Well, we have x and a positive y, which would be pi over 2. Or you can picture where that point is in your head, and you would see that 3 pi over 2 doesn't make sense. So this point then in spherical coordinates would be 4, comma, pi over 2, comma, 2 pi over 3. Remember that theta goes second, not phi. That's converting. So the next thing we need to talk about is how we're going to evaluate triple integrals. Questions on converting or the formulas or what any of those variables mean before we look at triple integrals? Okay, let's keep going then. So we are going to evaluate now triple integrals using spherical coordinates. I'm not going to spend a lot of time going through the entire derivation because I just don't think it's really worth our time. So here's what we're going to be looking at. We're going to be looking at a triple integral over some solid E, and we are going to have a function in terms of rho, theta, and phi dv. Definition-wise, when we look at a Riemann sum, this is going to be the limit as n approaches infinity, the sum from k equals 1 to n of f of rho of k star, theta of k star, phi of k star, delta v of k. And remember, the star just means that you can choose any point in that particular solid. So the question is, what is this going to be equal to? The question is, what is that going to be equal to? So this will become a triple integral with our function f of rho, theta, and phi. Limits-wise, we're going to go from rho 1 to rho 2, theta 1, theta 2. Convention, you do phi first. So convention is you're going to do rho, then phi, then theta. So if you remember when we did cylindrical, when we converted from rectangular to cylindrical, you had that extra r. In this case, what you will be getting is you will get rho squared sine of phi. And then you will have d rho, d phi, d theta. So every time you evaluate a triple integral in spherical, you're going to have to add that rho squared sine of phi. So let's look at an example. We are going to evaluate the triple integral over the solid B of e to the power x squared plus y squared plus z squared to the power 3/2 dz dy dx, where B is the unit sphere. So initially, we might be tempted to keep this in rectangular. What issue are we going to run into if we keep this with x, y, and z? You're going to run into two. Why is it not ideal to try to integrate this right now as it is? Okay, we can't integrate it because a u substitution isn't going to do anything for us. Beyond that, do you see that the limits of integration are not going to be nice? When you solve for z and then you're going to have a circle, so not nice. If we try to convert to cylindrical, which we could, that power of e, we would get r squared plus z squared. And then we would get another r. So potentially that's one way to do it. Like Jacob asked a while ago, though, does this only work for spheres? As soon as you see the word sphere, that tells you that you should put this in spherical. So that's what we're going to do. I'm not going to worry about the limits just yet. I'm just going to convert. So this is going to be a triple integral of e to the power x squared plus y squared plus z squared is rho squared, then to the power 3/2. As soon as I convert to spherical, I'm going to get that rho squared sine of phi, and then I get d rho, d phi, d theta. Okay, so our rho, because it's the unit sphere, is going to go from 0 to 1. Phi will go from 0 to pi. And then our theta will go from 0 to 2 pi. So that's what we're going to integrate. If we simplify this, this is e to the power rho cubed, and then I have rho squared sine of phi, d rho, d phi, d theta. And we have 0 to 1, 0 to pi, 0 to 2 pi. Okay, so then when I integrate this, if you consider a u substitution, some of you need to write this down, some of you don't. You would have your rho cubed. Your du then would be 3 rho squared d rho. So if you notice, we're missing that 3. So when I integrate then, with respect to rho, I'm going to end up with 1/3 e to the rho cubed sine of phi. And this goes from rho equals 0 to rho equals 1. And then we get d phi, d theta. Again, if you want to write down the u substitution, do that. I don't like to, but you can. Okay, I'm going to pull that 1/3 out. When I substitute in the rho equals 1 and the rho equals 0, I will get e minus 1 Okay, so then if I pull out that e minus 1 and I integrate the sine of phi, that'll be negative cosine of phi from phi equals 0 to phi equals pi. So then that will give me 1 plus 1. So then we get 2 times e minus 1 over 3. When we integrate with respect to theta, we get theta. So our final answer ends up being 4 pi times e minus 1 over 3. So I skipped a few steps, or did them in my head. If that's an issue, let me know. That is the idea, though. Questions for me? No? Is there something that I could have done at the beginning to arguably make this a little bit easier on myself? Anybody know?
Couldn't you have split it apart into different integrals? And then
Yeah.
just by one?
Yeah. Do you guys remember when I showed you that before, that you can do that? In this case, I don't think it really matters. In your homework, though, there are a few problems that it will make your life significantly easier if you split up the integrals. Remember that you can do that. Two things. First of all of your limits of integration have to just be numbers. You can't have any variables in there. And then you have to be able to split this up into various functions. So just keep that in mind for your homework. Okay, we got 2 more to do. So let's go on. We are going to convert the following to spherical. Outer limit is negative 2 to 2. The next one is negative root 4 minus x squared to positive root 4 minus x squared. Last one is 0 to 4 minus x squared minus y squared. And then we have z squared root x squared plus y squared plus z squared dz, dy, dx. Okay. We're not going to worry about the limits right now. Let's just convert this right now. Z is rho cosine of phi. The square root of x squared plus y squared plus z squared is rho. And then when we convert the dz, dy, dx, that's going to give us rho squared sine of phi d rho d phi d theta. Okay, so once we simplify all of that, that gives us rho to the 5th cosine squared of phi sine of phi d rho d phi d theta. Okay, when looking at your limits of integration, there are 2 things that you should recognize. You should recognize that these 2 limits for x and y represent a circle. You also should be able to recognize what these limits for z represent. Anyone? The limit for z? Sphere. Well, a hemisphere. Yeah. Okay, so visually what we are looking at is we're looking at the upper part of a sphere. That's what we're looking at. So then when we come up with our limits of integration, rho is going to go from 0 to 2. Phi is going to go from 0 to pi over 2. And theta will go from 0 to 2 pi. This is another one where you could split up your limits and it would make your life significantly easier. We are not actually going to integrate this. I'm going to tell you that it ends up being 64 ninths pi. We got one more to do. Any questions for me? Okay, we can go on to the last one. Okay. Last one. We are going to find the volume of the ice cream cone bounded by x squared plus y squared plus z squared equals z, and z equals the square root of x squared plus y squared. Okay. It is next to impossible to set up this problem without a picture. You need to know what both of those look like. Can anybody tell me even the general shape of either of those graphs? Come on, guys.
The fact that it's an ice cream cone, I'm guessing there's a cone.
Okay, which one is the cone? The second one. This one's a cone. Come on, anytime you see x squared plus y squared plus z squared, what's that going to be? Sphere. Yeah, this one's a sphere. It's just not centered at the origin. So if we want to discuss that sphere first, if we want to decide or figure out more about it, we're going to have to complete the square. So I have to add 1/4 to both sides, which gives me x squared plus y squared plus z minus 1/2 squared. Okay. Okay, that's what we're looking at. That is the ice cream cone. So you'll see that it's moved up, that the sphere is moved up a half point along the z-axis, and then we have our cone that starts at the origin. So that's what we're looking at. Okay. So if we set up for volume, volume is the triple integral of 1 dv. So I'm going to leave us some space for our limits of integration. When we convert to spherical, that'll give us the rho squared sine of phi d rho d phi d theta. Okay, I think the easiest limit to find is theta. We should be able to tell theta is going to be 2 pi. We have everything around that circle, so theta will be 0 to 2 pi. Okay. Phi and rho are more difficult to find. The closest distance we have for rho would be right here. The furthest distance we have for rho would be out to the sphere. So we're going to have to use the sphere to help us find our limits for rho. So if we take our x squared plus y squared plus z squared equals z, and we convert that to spherical, on the left side we get rho squared. On the right side we get rho cosine of phi. taking out a rho then, we get rho equals cosine of phi. So that is the equation for the sphere in spherical coordinates. So our rho then will go from 0 to cosine of phi. Okay. So then, last one we need to find is phi. Up here, our phi is 0. It's going to go all the way until we hit that cone. So the cone will give us the limits for phi. And you can see on the figure actually gives you what the limit is. But we're going to have to use the cone formula to find phi. So our cone formula is z equals that square root of x squared plus y squared. So z is rho cosine of phi. So then if we take x and we square it, that'll give us rho squared, sine squared of phi, cosine squared of theta. So all of that is x squared. And then if we take y and we square it, we get rho squared, sine squared of phi, sine squared of theta. So all of that is underneath the square root. Hopefully you can see if you factor out rho squared sine squared of theta, in parentheses it would leave you with cosine squared of theta, sine squared of theta. So that would then be the square root of rho squared sine squared of phi. So we get rho cosine of phi is equal to rho sine of phi. So then the question is, where is cosine of phi equal to sine of phi? That would be pi over 4. That's the only one between 0 and pi. So our limits then for phi are 0 to pi over 4. This one you cannot split up. You cannot split this one up because of the cosine of phi. Questions on how I found any of these? Jacob?
How do you find the rho cosine of phi equals rho sine of phi?
So you would divide your rows out of each side. So then you need to figure out where, for what angle, is cosine the same as sine.
Oh,
Okay,
okay.
beautiful. I'm going to move a bunch of this out of the way so we can oh, okay, cool. We are going to continue our integration down here. So we have 0 to 2 pi, 0 to pi over 4. If we integrate our rho squared, we will get 1/3 rho cubed sine of phi from rho equals 0 to rho equals cosine of phi. And then we get d rho d theta. So when we substitute then, we have 0 to 2 pi, 0 to pi over 4, and we have 1/3 cosine cubed of phi, sine of phi, d phi d theta. Again, you have to picture a u substitution. U is your cosine of phi, so then your du would be negative sine of phi d phi. So hopefully you can do that in your head. If you can't do it in your head, write it down. When you do that integration then, it would give you negative 1/12 cosine to the 4th of phi from phi equals 0 to phi equals pi over 4. Okay, so then this will give us negative 1/12. Cosine of pi over 4 is root 2 over 2. Cosine of 0 is 1. I'm just going to go horizontally because I ran out of room. If you trust me on that calculation, that's 1 over 16. So then our final answer ends up being pi over 8. And remember that that is the volume of the ice cream cone.